Good morning, everybody. Glad it's now working. Anyway, so this presentation is about hardware. It's not actually about software at all. It's in, well, there are two main parts, a little sort of brief introductory one, not really a part at all. But I just want to briefly mention the scope and objectives and the hardware requirements and support requirements because they determine the hardware that was chosen. So part one will be about the hardware, an overview, concentrating quite a lot on antennas and rotators because our kind of standard equipment is a bit larger and heftier than some amateurs may be used to. I'll briefly mention the other ground station equipments, and I'll have illustrations from ISU, which is the International Space University in Strasbourg. Then part two is about ground stations, a bit more detail, and actually quite a lot about what we're doing at ISU. I don't work for ISU, I just happen to be installing it there on behalf of the GENSO project. So we're talking about the roof, the building antennas, problems, bit of interference with their radio astronomy dishes and things like that, and then finally what are the next steps. So that's an overview of the presentation. Firstly, the scope of the hardware. Well, it's civil, it's university, mostly amateur satellites, Amsat type satellites. Science, civil, it's not at all military. We definitely want telemetry, CW, mostly beacons, audio, that's good, and some satellites, such as Cal Poly, can do photographs and images as well. Data is definitely not hidden, not encrypted, not secret in any respect at all. And the IOU and the national band plans very much apply, which that determines the frequencies used for the hardware. So what's out of scope? This is just setting the general context. It's not commercial, it's not navigational satellites, it's not marine satellites or Iridium, although Neil was tracking a couple of those just as examples. Nothing to do with NOAA or weather satellites or TV or radio or military or intelligence or anything of that kind. So that's the general context of what we're doing. Now, the primary objective of the GENSO hardware is to send commands and also receive telemetry to and from these satellites, as I said, university and amateur satellites. The requirements in more detail, which determine why certain hardware was chosen, is they have to operate at these frequencies, the IRU, RU amateur bands, definitely VHF and UHF in 2 meter and 77, both up and down link. L-band, not all sites necessarily will have this, but the sort of more flagship ones will, so it's up on L-band. Right now it's down only on S-band, but in the future, well, who knows, and we're things like 10 gigs and stuff, maybe the Mars mission, we might mention that later on. So it's all possible. Modes, well, all kinds of modes, voice, CW, beacons, data, SSTV, various things. The speeds are primarily common amateur speeds of 1200 and 9600 bits per second, and for some 38.4 for images, but it's a bit more advanced. This protocols, I regret to say, Akim, it's the standard AFSK and FSK type protocols, but universities, as we've seen, like to write their own protocols and telemetry, such as AAU, also such as Delphi. So we can do that as well, but it may need a bit of software, and who knows what's coming in the future. Orbits, well, mostly low Earth orbits, so it means very rapid tracking, quick pass, 10, 15 minutes, so we need good tracking. A few high Earth or highly elliptical orbits, whenever it gets launched. Nonlinear or extremely eccentric type, nonlinear type orbits. Geostationary, well, it could. Just pointing at one fixed place, rather a waste of a good tracking system, but you could point to one particular one, and I think Amsat in the States announced something along those lines, so it could do that as well. Moon, well, yes, it can certainly track the moon with the right telemetry, and looking at, I hope, not too far ahead. It can definitely do this as well. I had a very interesting chat with Akim the other day, and this size of dish can do a lot for the Mars mission. But the cost is a very important constraint. It's sort of a loosely high-end amateur range. It's definitely not commercial level, and let alone NASA type level. It has to be affordable by by universities and by let's say high-end sort of amateurs. So that's a rough idea of what the cost has to be, and it has to survive the local conditions. In the northern latitudes of Europe and Canada and the States, that means snow, ice, high winds, and that sort of thing. It only takes one accumulation of freezing rain on very long antennas till you find them, they're broken next morning. So once is enough. So we've come up with an H-frame design, which I'll talk about that. So it has to survive in worldwide conditions. Now, in more benign areas, such as California, where it's it's sunny all the time, you can have nice long antennas, and you don't. Of course, there's a fire risk, but you don't have the same kind of problems. Another constraint on the hardware is it should be available more or less worldwide. It's no good having something wonderful, but it's only in one particular country. So we're talking about major brands which have to be tough, reliable, well-proven, and supportable. It's not kind of new stuff that's wonderful, for a few days and then needs a lot of fixing. Now, the software type of support requirements for Genso are also important here, because the Genso software has to be supported worldwide from such as Aalborg and Vienna and the UK and various places. So the software will be tested and supported on a small number of well-known and well-proven hardware configurations. So we're talking about a standard hardware list is required to enable software support and therefore worldwide support. But it is not mandatory. Every other kind of hardware station with different hardware is very, very welcome indeed. But trying to support that with, well, it could be difficult if we just talk about a small number. And then if you've got hundreds of different hardware configurations, it's probably an impossible job in the realistic terms. So for non-standard hardware, well, I'm sure we'll help with problems, but it could be a bit of a do-it-yourself job to fix them. So that sort of sets the tone for the hardware that we're talking about. Well, it's better than this. I mean, this looks like it used to be a log periodic at some point, but there are quite a few pieces missing here anyway. So the presentation is mainly about the antennas, the pedestal and the frame for it. I've been corrupted by the US, I'm afraid, and I tend to say rotors now instead of rotators, which is the proper word for this stuff. The big H-shaped frame which we'll use to support it, the controllers, just briefly about the radios, preamps and all the small things. I mentioned those as well, and the type of cable we're using, which is a pretty good low-loss cable. Okay, this is what it will look like, the antennas. Now, this guy is supposed to be to scale. I got him off the web, so this guy's 6 feet tall, and this vertical pedestal here is 6'3". So that's supposed to give you an idea of the scale. We got two VHF antennas, pair there. We got two UHF antennas, and we designed in the mathematical modeling, design point includes a 1 meter dish. Actually, in the first configuration, we'll probably only have a 60-cm dish, but mathematically, this thing can cope with a 1 meter dish, so without screwing up the antennas much or at all. And that's the rotator. These black things are the motors and the rotators, so this is the rotator and the other one. Maybe this is a slightly clearer view. Again, this is to scale, so that's 6'3" to there. That's the azimuth rotator bolted onto this. There's the elevation rotator. 1 meter dish, UHF and VHF side. When the antennas, these are now pointing horizontally in this diagram, but when the VHF antennas are oriented vertically, then the tops of them are about 16 feet above the ground level, because these are actually mounted on a frame. There's about 2 feet here. So the whole thing is actually quite big. These are the antennas we're talking about. The manufacturer is M Squared, or M2 in California, who make a wide range of amateur, commercial, and NASA-type equipment. So they're very experienced, and they've got a very good design team. So it is good quality stuff. We've got a pair of CP14s, and that's the gain, and that's the half-power bandwidth. We got a pair of, at 77s, we got a pair of CP30s, these ones. Again, that's the gain, and that's the bandwidth. So it's fairly narrow kind of band, but then we've got very accurate rotators. Accurate, I think, to about half a degree, can point them well, of course, as long as the software is up to it, but I just assume that to be the case. This is the H-frame, this green thing. I don't know why it's green, but anyway, that's what the H-frame is all about. And there's also a T-brace, which are extra supporting rods. Don't show well at this angle, but they're to stop. If you've got two antennas as a pair here, to stop them sort of wobbling around in this direction, you've got a vertical rod and another supporting rod. That's what the T-brace is. So that's the whole collection of bits. So that's what it looks like in real life. This is just the base and the 6'3" rod, and just peeping out of the crate, you can see there are angle irons that go in here and connect to these lugs. So it'll be built in the case at ISU. It'll be built into a very heavy metal grid and frame, which weighs 600 kilos. There's more than half a ton, according to the architect who's designing the thing. So he really ought to know. So they wonder if it's actually worth screwing to the roof, because it's weighing half a ton anyway. It probably isn't going to blow away. So anyway, we'll fix onto that. There are bolt holes in here. This roof is quite high up and exposed, and the recorded wind speeds have been over 100 kilometers an hour. But the design point for these antennas and pedestal is over 100 miles an hour, 160 kilometers. So it's supposed to withstand winds of those speeds without damage, which is well above hurricane force. So we're talking about very strong winds. And if it goes faster than that, well, and they blow away, well, you just buy another one, I guess. So the rotators are also pretty tough. There's a reason for that. Part of the concept of Genso is this passive receive mode, which even if nothing is scheduled, and Neil maybe correct me if I'm anywhere wrong on this, even if nothing's particularly scheduled for a pass, the scheduler can look for any coming up, an upcoming satellite, and decide to receive telemetry kind of all day long by itself. So this could, in certain places, certain ground stations, could be semi-constant use by Genso, a lot more than average. So we're talking about, we need very heavy gears, heavier than the average kind of gears, and this is a worm on here. We want long life. It wants to be field maintainable. This white thing, or that box there, is actually a motor, and you can just undo these bolts and take the whole thing off and put a new motor on as a spare, without having to take the entire rotator to pieces, which is normally the case. So this is a better design for field maintainability and general long life. So it's very tough, and okay, it's very strong. There it is on the floor. This time last year, I was in California in the factory, and there is a pair of rotators on the floor, and the vertical pedestal goes up here, and then the cross boom goes across the top through that. So that's what it looked like in California, and I'm pleased to say this is what it looks like in the crate when we unpacked it at ISU in Strasbourg. That's the model. M2 or M squared is the company, and there's called ASL1000, and there's a pair of very similar rotators, but the fittings are slightly different. So just a quick reminder of where it all fits. They go on here and they go on here. So we've got this H-frame and the T-brace supporting pairs of Yagis, which we've been constructing last week. Okay, this is, we laid it all out on a classroom floor. It's all quite big. This metal ruler here is 2 feet long. So that's 3 feet, that's another 3 feet, that's another 3 feet. Plus you lose a little bit of the join. So it's more or less 9 feet up and down on the VHF side. There's the cross boom, which is very heavy. I know it's aluminium, but it's extremely heavy aluminium. I just got a couple more photos like this. So that's a sort of a vertical view. Well, actually that's the floor, of course, but you can imagine it's the sky, and you're looking at it kind of sideways if it were up in the air. I hope that makes sense. This is fiberglass, so as not to interfere with the radiation pattern. That's fiberglass too, and this is on the UHF side. It's completely fiberglass. So it was all heavily modeled by by m squared. Oh, well, that's just what the bits at the top. I'll go through these quite fast. You can just see that they're pretty big, heavy things, and same thing from a different angle. Okay, these are the controllers. Normally they come as two separate boxes, but they can be fitted into one cabinet ready for rack mounting, but there's no difference. They're two separate controllers with a little tiny ribbon cable between the two. That's the model. They support these rotators. They work obviously manually or by PC program control. They are multi-speed. A lot of rotators only have one speed, which can lead to sort of juddering effects, as James Miller was telling me about this yesterday. So if you only have one speed, it tends to sort of do this and shake a bit, and then it does that and shakes a bit, and which is not good for tracking your satellites. These have 4 speeds, at least, anyway. They've got sort of fast, medium, slow, and very slow, which you can select on this button, which is good for very precise, slow, gentle tracking. So this is a plus factor. It's got a mode button. Dave knows about these modes. He's been writing the software for it. So you can go clockwise, anti-clockwise, or on this one you can go up and down, and again it's got speed buttons. So it can be, work manually, and the ones we've got in just arrived in ISU work fine. And for S-band, optional, but we hope a lot of people will have it. It's as I said, it's designed to have an up to 1 meter dish, but we're probably going to have James Miller's 60 SEM or 2-foot dish with a patch antenna, which works very well. In fact, it even works without a dish. There was some talk, someone was holding up to the sky just by hand like this and receiving, I think might have been Oscar 51, but it's an extremely good antenna. Because the radio doesn't directly receive S-band 2400, it needs a down converter. We're just talking about down only in this case, although we could use a transverter to both go up and down. So it'll be down converted to, say, 144 or something. This is a model. And so that's S-band. Sorry about this rather fuzzy picture. This is for L-band, which is uplink only. I got it off the web. Actually, this is the short one. They make another one about twice as long. Same thing, but it's a longer helix for a bit more gain. I didn't find a picture of that. So that's what the L-band uplink helix will look like. Here's the radio. We're talking about supporting two radios initially. In fact, this is the only one. The ICOM 910H is the only one that can be bought new these days. The ASU 847 is very widely used and liked, and it's an alternative radio, but it's not available new. So I'm sure we'll have support for it, because a lot of us have it. Cal Poly have it, I have one, various people have one. But that will be the standard radio. Doesn't mean that you cannot use more expensive ones, different ones, like a TS2000, but they aren't really satellite radios, and that support for those will probably come later on. I think we won't go into that detail. These are the smaller kind of bits. We'll have a preamp. SSB is the make again. They are available worldwide. They're actually made in Germany, therefore available all over Europe, but they're also sold in the States by SSB Inc. So they're available all over North America and other places. So it's pretty well worldwide, very weatherproof, well sealed. We'll have that model for VHF, that model for UHF. These are the sequences that really protect this from being, if you're blasting 100 watts or something into your preamp, not a brilliant idea. So these put them in bypass or out of circuit. Be 2 of those. The TNC for 1200 speed and 9600 is a Cantronics 9612 Plus. It's got a few extra bits in it. And then for 3400, the Cymec, this TNC. But this will be more or less the standard model. Cables we're got again from the States. It's Times Microwave LMR 600, which is a very good low loss kind of cable. The loss per 100 feet at VHF, I think it's 0.9, and for UHF it's about 1.7 approximately. So it's very good low loss cable. well, I just said that. For S-band and L-band, because we're buying that kit in Europe, we've got EchoFlex 15, also very low loss cable. There's a reel of it there. And this is sort of a multi-core cable for things like the polarization relay to switch between left and right hand polar CP, DC power supplies, 12 volts on and off, that kind of a thing. We'll also have a cable, actually on the roof they've already got a lightning pole and lightning ground, and we'll have webcams like here, and both in the radio room and on the roof, but I think it'll be a real webcam, not a picture of a TV picture of something else, so it'll be better, better quality. Okay, that was also general hardware. This is illustrations of the actual stuff more about at ISU, which is in Strasbourg, France. I'm glad to be able to report that since last year, we've got some real actual hardware progress to report. The stuff is there, and the ground station is in the process of actually being built. The next station is expected to be an STEC soon, I don't quite know when. But of course, there already are some existing stations already running, like Cal Poly had theirs running for years. I didn't know how many years, but a long time. And Aalborg had been running again for quite some time. Davis has his running, and Graham over here has recently installed some new kit, and that's all up and running, doing very well. So that's the first new one for Genso, but these are all other good ones. I keep mentioning ISU. Well, what is it and what do they do? Well, it's a postgraduate university. It's relatively small, as universities go. They teach master's courses in various space subjects. They've got alumni in a lot of different organizations. They also perform radio astronomy experiments on the sun, a lot, Moon sometimes, Jupiter, special thing for Jupiter, and different parts of the galaxy. They're very kindly allowing us to use their radio room and their roof space. And I must say they've been extremely helpful, really very positive, very cooperative, and supportive about getting the whole thing off the ground. We've had some potential problems, such as interference from Genso transmissions with their radio telescope dishes, because we transmit quite strong signals, and they want to listen to very weak ones, so we could actually blow the front end very quickly. Am I running out of time? Okay, okay, well, okay, I'll speed up a bit. That's what it looks like, kind of modern, futuristic. We're going to be putting on our kit on the roof here. The radio room's in there. This is actually 4 floors. The radio room is kind of through that wall, and we'll be up on the roof. And the big dish that they were going to put also on the roof is now going to be put on this roof behind the library. So we hope the library will actually protect it from being damaged. We've got this whole block. But we have to do some experiments to actually measure the signal strength. Okay, well, I'm going to speed up here. It's, you can read it. The weather conditions there, actually, it's between a couple of mountains, 2 sort of low mountain ranges. This is what it looks like in the winter. There's something like 5,000 trails, including cross-country trails. So you do get very nearby snow, ice, and strong winds. And when I've been there, I think it's been lightning every time. The air mass tends to get trapped between the mountains and can't escape. So lightning is actually quite frequent there. So that's a consideration. That's what the roof looks like. We're going to be putting our equipment in this empty flat area here. This is what the heavy framework I was talking about. These are big, thick girders. And it'll be mounted on girders like this, but very much bigger on top of this grid. We're going up on a crane. They're lifting this half-ton thing up on a crane so we can lift our kit up at the same time. That's a small dish they use for sun radio astronomy. Even with these buckets full of concrete, it's blown over more than once and bent the arm, which was a bit of a surprise to the students when their experiments didn't quite come out right. But it just proves the point about the winds. Okay, I won't mention that. That's the new dish they're going to install. Building the things, well, you get these, it all arrives in these great big crates, and it's really factory-type work. We had to re-drill the boom because one of the parts was wrong, and so there we are drilling new holes in the VHF boom, using the other one as a kind of a model, and putting the polarity switch on. That upgrade was a lot more complicated than you might think, because we've got to take some elements out and move things around. And I'm going rather fast now. So we've just built 4 antennas at ISU. There's 1, 2, 3, and another one up this end. So they're ready to be put on the roof when we've installed the rotator. This is the room we're going to be in. We're going to be in that alcove there. These pieces will be moved. So it's a nice big empty room with lots of space, which is great for us. And next steps, well, you can read them if you like. I think you want me to wrap up, so I'll wrap up. So these are the things we've got to do next. Build it all, carry on, finish off building it. And I won't do a summary. This is our next ground station. After that, each one weighs over 200 tons, and there are 27 of these. It's the VLA in New Mexico. So you've got to think big. And that's the end of it. That's supposed to be a live photograph. But anyway, no questions? Or anyway, I finished. Thank you.
We time for just
one question.
I've got one as well.
Sorry, could you give us an indicative price of such a great ground station?
The approximate price. I think we had a budgetary figure of about 30,000 euros, but Neil may well correct me on that. But that was just for the, that was about a year or so ago, and that was for the hardware only, without any work of installing it.
20,000.
20, there you are. I'm good at hardware, but not so good at numbers. 20,000 per ground station.
The question I had from the internet was the same, but they were really just asking about the antennas. What does that cover, the 20,000?
Kind of all of it, including the radios and all the small bits, not just the antennas. It's the whole, it's everything you need, including some cables. Yeah.
Okay, I'd like to thank John for a very good talking to you.
Thank you.